Integraph and Dynaflow Research Group. Today's webinar is an introduction to BOSfluids for better fluid flow analysis and see how you can benefit. My name is Chris Bradshaw. I'm Business Development Specialist for Integraph CADWorks and Analysis Solutions here in Europe. And I'm pleased to say I'm joined today with Richard Fawcett, who is a project engineer from Dynaflow Research Group. Would you like to say a few words to introduce yourself, Richard?
Yeah, hello. As Chris said, I'm Richard Fawcett from Dynaflow Research Group, and we are consultants that use BOSfluids in our consultancy assignments, but also we're the developers of the software and have developed it based on our consultancy experience.
Okay, thank you, Richard. So let's start today's webinar, and first of all, let's take a look at what is surge and water hammer effects, and then we'll see how BOSfluids can help, and then we'll take a look at a real-life example from Dynaflow Research Group. So, the effects of the fluid flowing through the pipeline can often be overlooked when performing the mechanical stress analysis of a piping system. However, the effects of the fluid flowing through the piping system can often be significant. As we can see here with a few images, we have a few situations which have occurred which are, shall we say, a not desirable situation. On the left-hand side, we can see the cloud highlighted there is actually where the pipe has collapsed due to a vacuum situation which was not accounted for. The image in the middle shows the pipeline which was highlighted there in red, which should be sat on the pipe rack along with all of the other pipes. Something has happened which has caused that pipe to jump and is now sat resting on the other pipes rather than sat on the pipe rack where it is supposed to be. And the image on the right-hand side shows quite clearly that the steel member there has become deflected and has bent out of shape, and also the pipe support has actually become sheared and has failed, again due to some high axial loads that weren't accounted for, all caused by the fluid flowing through the system. So as we can see, accidents can and do happen when a surge analysis is omitted from your piping analysis. So what is a surge event? Well, a surge is simply a variation in pressure that is generated by a change in the operational status of the system. These surges, they may be foreseen situations such as a pump startup event, or it might be an unforeseen operational change such as maybe a valve closing quickly causing a hammer event, or a pump trip event, or even a change to the pipe layout may cause a surge event to happen. These surges can lead to unanticipated effects such as extremely high or low pressures in locations through the system, or lead to pressure imbalances which can lead to an unbalanced force, and that can lead to pipe movement. So what type of events may lead to these situations? Well, here is an example of a few different types of surge events. You may have a very high pressure which can lead to permanent deformation or rupture of a pipeline. Converse to that, a very low pressure may cause collapse of the pipeline like we saw in the image shown earlier. This may also cause leakage at joints and seals under subatmospheric conditions. Reverse flow in the pipeline can cause damage to pump seals and brush gear on motors, and can also inadvertently drain storage tanks or reservoirs. A pressure imbalance along the leg may lead to pipe movement and unbalanced forces. Acoustically induced vibration can lead to pipe movement, and you may end up experiencing resonance, and that can lead to overstress of the pipe or failure of the supports. And a problem that is particularly prevalent in a slurry line is if you have slow flow rate, that can cause settlement of an entrained solid and lead to a blockage of the line. So, in summary, a surge is basically a pressure wave running through this piping system. And what happens is pressure at a particular location or a system node in terms of our analysis model can vary over time due to a wave passing by and being reflected at the end of the system. These pressures can rise to very high levels, as we can see in the chart here, from a steady state situation in the chart of around about 17 bar pressure. We have a very high pressure spike where we have hit around about almost 26, about 25 bar pressure. The opposite effect of that is this pressure spike may be a low pressure spike as well. We may see a very, very low or even a negative pressure shown here, which can lead to, as we saw in the image, a vacuum condition which may lead to pipe collapse. So here are some examples. We've already seen these, but here are the examples, some examples in a larger size image. Here we have seen some transient effect has happened. We have had a surge event, and that has led to axial movement of the pipe. The pipe support shown here was not designed for that high axial load. The pipe support has broken and it's failed, and the steel beam highlighted there has deflected due to the high axial load that was not designed for. We've already seen this example as well. The pipe that is supposed to be sat on the pipe rack along with all the others has moved significantly. You can see it's not moved a short way, it's jumped over the first pipe, and it's now actually resting on around about the second pipe due to some unforeseen unbalanced forces, which again weren't accounted for during the design. Here we have an unforeseen vacuum situation highlighted in both the red and the black clouds shown here. Again, this is similar to what was shown in the chart, although in the chart we had a high pressure situation. Here we have a low pressure situation, an unforeseen vacuum, and the pipe has collapsed. And finally we have another issue here where again we have imbalanced forces, and the pipe shown here lifted from its support, highlighted in red, once the support has been deformed. So a high axial load deformed the pipe support, and then the pipe lifted and jumped off of its support. Again, very high loads that were not accounted for during the design. So we've seen all these situations that can occur. Accidents can and do happen due to this, and this is where BOSfluids comes in. How can this help us? Well, BOSfluids can be used to evaluate these transient events, the surge events, and BOSfluids can predict the effects of those events. So let's take a short look at the capabilities of BOSfluids as a general overview. BOSfluids includes both a steady state solver, which can be used to determine flow through the system, pressure drops, and velocity distribution throughout the system. We include various types of components in BOSfluids, such as pipes, valve, orifice, pumps, and many more. In addition to the steady state capabilities, though, BOSfluids also includes transient capabilities. There is a transient flow solver which can determine dynamic flows, pressures, velocities, and imbalance forces throughout a system. The solver is based on a reliable method of characteristics, so it's reliable physics, and also included is a part multi-phase analysis capabilities as well, which includes elements for things such as cavitation and air inflow into the piping system, and also outflow for drainage. So BOSfluids, with these capabilities, is suited to many common flow problems. There are a number listed here, which I'm not going to read through all of these, but as we can see, there are various different analysis types. Steady state, which BOSfluids can be used for pipe sizing or pressure loss analysis, or for generating pump specifications rather. And also transient analysis types, as I've mentioned, things such as a water hammer analysis or a surge analysis, a tube rupture on a heat exchanger as well, and the other transient events listed here. With these capabilities then and these different analysis types, BOSfluids is suitable for many possible applications and is used in all these applications and more. Things such as a sewage water system, high pressure heat exchangers for simulating tube rupture, LNG systems, and many more. And as I said, BOSfluids is used throughout the world on systems such as these. And it is used because a manual calculation to simulate the effects that BOSfluids calculates is simply insufficient. On the right-hand side of this slide here, we have the commonly used Yukovsky simplification, which calculates the change in pressure here, delta P, by simply multiplying the speed of sound of the fluid, C, multiplied by the density, multiplied by the change in velocity. This is a very conservative simplification, and compared to the detailed results from BOSfluids, you can see much difference. We have one value that comes out of the Yukovsky simplification, the delta P. Compare that to the detailed BOSfluids results, where we can see the change in pressure as the pressure wave reverberates through the system with the initial high peak, and then as the pressure wave decays as it flows through or reverberates through the system. And one of the larger advantages of BOSfluids is that it can be used in conjunction seamlessly with Caesar 2. We can perform the surge analysis of the varying different transient events in BOSfluids, which will then predict the forces throughout your piping system. And these forces can be taken and used in a mechanical pipe stress analysis, such as Caesar 2, to perform your dynamic analysis of your piping system. The direct link between Caesar 2 and BOSfluids, which is a bidirectional link, works together, and it makes this a lot easier than doing manual transposition of data and manual transposition of your piping system. So how does this work? Well, here's a simple example. The model you can build in Caesar 2 and perform your static analysis as you would do today. So build the model however you build it in Caesar 2, do your static analysis, and then you can generate out of Caesar 2 a Caesar 2 neutral file. Standard Caesar 2 capability. That new Caesar 2 neutral file can then be read directly into BOSfluids. And your piping model is now available in BOSfluids for your steady state and your transient event analysis, using a direct transfer in just a few seconds. So once you have your pipe model in your BOSfluids module, you can then define the boundary conditions for the steady state analysis. These are things such as a fixed pressure condition or a fixed flow rate throughout your system. And then you can also define parameters for a transient event. In the example shown here in the images in the presentation, this is a sudden valve closure. So we have the valve which comes through from the Caesar 2 model when it's defined as a rigid in the Caesar 2. And then we can specify the valve parameters for the valve closure event. Things such as the CD curve can be specified. Here is a larger version of that image. So you can specify a CD curve as how the valve opens, and you can also specify the timing of the closure event in the valve as well. And once you've specified that information, you can then perform the BOSfluids fluid flow analysis. Here is an example of a small selection of the type of results which we get from BOSfluids. We can see in the top left-hand corner that there is a pressure wave reverberating through the system. You can see the changes in pressure through time as the animation plays. So this 3D output can be used to show various parameters. The image is showing pressure on the top left. You can see the other types of results that we get in the bottom right. And these can be shown for the duration of the transient analysis and played back as an animation, as shown on the screen here. And in addition to the 3D output, there is also a 2D output available up to 2D charts, which can be used to plot required results at any location in the system. In the example here, we can see the forces in the system over time. So this is a force versus time profile. And you can plot multiple charts on the same graph to plot whatever you need to view. There's varying scenarios, varying data sets of results, varying locations in your system. All can be plotted on the same graph, so you can see and compare multiple situations very, very quickly and easily. And then this data can be used in Caesar 2. So it's very simple to see the maximum values to check if an event may cause an issue. So here we have a zoomed in version of the image shown before where we have the animation. This is now the static image showing the maximum force. And here we can see from the chart that, from the image, that the fluid hammer, it causes a force here up to around 90 kilonewtons. And high loads such as this may well be a concern. Now, just before I go on to explain what we do with this, one thing which is very useful is a product called BOSview, sorry, which is a free viewer for your BOSfluids results. And Richard, would you like to discuss BOSview, sorry?
Yeah, so BOSview is similar to, has the same output interface as BOSfluids, but it doesn't allow you to change the input interface. So if you do your simulation with BOSfluids, then you can send the BOSview file, and then your client, instead of getting, in addition to a series of 2D plots, your client can then choose to view the pressures, the flows, at any point in the system, at any point in time, so that if they want some additional input information that maybe you didn't include in your report, they can view it at their own leisure to see all the results through the entire system. So you can view this similar as the same as Adobe Acrobat and Adobe Acrobat Reader. So, and this can be downloaded free of charge from our website at any time.
Yeah, so this is a free viewer that can be supplied, or you can supply your BOSfluids results to anyone, and they can review the results using the exact same viewing capabilities as in BOSfluids. It's just that they can't change the system, can't change the analysis. Okay, so once you have your results from BOSfluids, the image that was shown a couple of slides ago was the force versus time profile. And once you have that force versus time profile, you can then export those forces for use inside Caesar 2. BOSfluids generates a file format, a .dat file, which can be read directly inside Caesar 2 to create the force time profile for a dynamic analysis. It's a very simple process. You simply select the force pairs to export. This is the varying elbow pairs that you are interested in, which is typically the longest leg throughout your piping system, although there is no reason why you couldn't do every single leg in your piping system, because it is an automated process. Then once you've exported the .dat file, that can be read into Caesar 2 in the dynamic analysis module, and you can perform a time history analysis. It's a simple matter in Caesar 2 of clicking the Read from File button and opening the .dat file as relevant. Then you complete the setup of the dynamic analysis, apply the correct force time profiles inside Caesar 2 at the correct node numbers, and then run the Caesar 2 dynamic analysis to see the results of the effects of the flow of the fluid through your system in your mechanical pipe stress analysis. Okay, so now, Marjolaine, could we have the poll question, please?
Yes, it's available now on screen, Chris.
Okay, thank you. So the poll question is available now. The poll question is, as you can read on your screens, how frequently do you perform a surge analysis? And the answers are never, very rarely, only retrospectively when an issue has occurred on a pipeline in operation, or often.
All right, thank you, Chris.
Okay,
so now the results are available. So 24% of participants have answered never, 48% have answered very rarely, 12% have answered only retrospectively when an issue has occurred, and 16% often.
Okay, thank you, Marjolaine. Okay, so the results from the poll question are broadly what I expected, and it shows that around about three-quarters of people either never or very rarely perform a surge analysis. And that's very interesting because, as we've seen from the small images at the start of the presentation, that accidents can and do occur. Now, the images I've shown were, shall we say, they weren't major failures that happened, but the failures can certainly be major. So I'm going to now hand over to Richard from Dynaflow Research Group, and Richard will take us through a real-life example where a more serious failure did actually occur. So Richard, I'm going to now give you control of the presentation, and I'll let you take over.
Thank you for that, Chris. Okay, thank you for that, Chris. So as Chris said, we're now going to discuss a real-life example based on a project that we conducted a few years ago here at Dynaflow Research Group. So let's go through to the slide. Okay, so what you're seeing here is we've got a pipe running across horizontal, and we see there's a big gap in the piping. Okay, you see the piping was connected with a series of ring couplings, and the question first of all is, why did this failure occur? Well, let's first of all look at it actually occurring, because due to some videos that were taken during the test procedure, we actually managed to capture when it failed. So I apologize for the quality of the video, given the video was not set up to record the failure. What you see, the pipe is running across the top from the almost vertical through the screen, and you're seeing there the explosion as the coupling fails and the water is spraying out of the system. Let's just review that again so we can see the moment as it happens. Line once again moving vertically, and you're seeing the force of the water as it leaks out of the system. As I say, this is a cooling water system, a firewall system, sorry. So it wasn't like there was oil leaking out, but still. Okay, so let's have a view of what the system actually looked like, and this is an overview based on the BOSfluids model that we built of the system. First of all, the water enters into the firewall system with the pump, going from a tank into the pump, and then moves along the line, like so, comes along, and then it comes into this section here, where there is a sprinkler connections, which you may have noticed on the previous slide, the red valve, which is connected to the smaller sprinkler system. Okay. At the end of the system here is an air bleeder valve, and this air bleeder valve is used to bleed off trapped air, which begins to fill the system when the system is out of use for a significant amount of time. And we can see the locations of failure was shortly upstream of the air bleeder valve. Say failure occurred during the testing of the system. So if we go back, what was happening in the tester is this section of line had largely filled with air, and when they were testing the system, they wanted to first of all bleed all the air out of the system. So the air valve was open, and the air was bled out. At the moment the system stops, at the moment the system is totally full of water, and the air stops flowing out, and then it's just full of water. And they wanted to test what would happen at the moment the air valve closes. Take a look at a few photos. What you see here, these are the locations. You see the red is the time points for the sprinklers, and this is the coupling joint that failed. We notice the pipe slightly to the right, and let's see from another angle. You can see here, just right and above of the one, this is the 45-degree section where it failed. So let's look at the BOSfluids model in a little bit more detail. We had the pump boundary conditions, and then BOSfluids included the resistances in the system. So we had the hydrostatic head. You know, if you go for 10 meter high, then you generate additional 1 bar pressure drop, and also the frictional losses through the pipe lengths and also through the bends. Then additionally, the valve, the pressure losses of the flow passes through the valves in this area of the system. And we pass down to look at the air valve at the end of the system. Okay, the pump was modeled based on the data supplied by the client, and we see here's the pump curve, and what happened is from the pump curve, it is shown here as a linear profile, but actually the system will build up a quadratic curve based on the 3 points that you've entered, and the pump will then move along that curve depending on the back pressure in the system. So if you have more friction in the system, then the flow rate will decrease through the system. Then at the end of the system, we have the air valve, and with the air valve, we want to simulate the moment where the air valve closes, because all of the air has passed out of the system, and then it's seen as the approaching water column. So if you see here, we estimated that the valve would respond at the order of a tenth of a second, and you see here the valve closure goes from 100% to 0% in 0.1 of a second. So the question, what was our hypothesis why the failure occurred? Well, what we say on the left is the liquid column comes in from the pump and begins to compress and push the trapped air out of the system. So through the air valve is largely a very small cross section, but the air can pass out of that small cross section. and the liquid column approaches at a very high speed. So it's the difference between the pressure, the head supplied by the pump, and atmospheric ambient air. Okay. When the liquid column reaches the valve, because there's only a small cross-section area available for the air to bleed out the system, then the fluid column will be stopped. And in stopping that leads to a large water hammer peak. So what we're going to show you with this video is a BOSfluids simulation of the failure. So what I'm showing you here, if you can see where my mouse is hovering, you see the 45-degree section. Okay, and what's happening? You see the pressure in the system is around 2.5 bar to start the system. You can see from the color code. Okay, and then what you will see is the pressure slowly starting to rise due to the wave that's reverberated back from the air valve. Whilst on the left, you will see the failure occurring in the line. Let's play the video. See, the pressure is rising. It's now at 3 bar. It's now rising up to around 4 bar, and now reached around 6 bar, and then you've got your failure. Then move back, and we can see the water gushing out of the line. See here, the water leaking out. Let's play back. So move back through the film a little bit. So see again, you can see the pressure rising. So these films you can always play back in BOSfluids at any point to see what's happening. And we see there the failure occurring. In the line. So, first of all, we've shown a pressure rise, but the question was that significant to cause the failure that we saw? Well, the coupler joints had a pressure rating of 20 bar. So we estimated that then they would have a failure pressure of around twice that. So we took 40 bar to be the failure pressure of the coupling. So what happened once the pressure reached 40 bar? Well, this is then not realistic because the line had failed. So how could we model the fact that a line had failed? So what we've done is we added a valve or a break in the line. And once the pressure reached 40 bar, then we opened this valve, and you see then, by the red line, that the pressure drops down to 0, because now we're connected to the atmospheric air. Now, why did we want to account for that failure of the coupling? Well, it's important because we wanted to analyze the correct case for coupling with Caesar 2. Because we wanted to see how did the system respond mechanically to the unbalanced forces caused surge events. Were there going to be stress problems, other couplers that had issues, or large restraint loads? So we built a model in Caesar 2 by exporting the geometry from BOSfluids, and then we added a series of restraint points. As we can see here, series of restraints in the system, and the mechanical properties, the material properties, elastic modulus, into the system, to the model. We then wanted to ensure we exported the unbalanced forces from BOSfluids into Caesar 2. So we coupled the elbows, for example, these ones shown here by the green arrows, to calculate what was the pressure difference and therefore the unbalanced forces between these two elbow pairs, which we can see on the right, and then we exported those into Caesar 2 in a time history solution and applied that to the nodes in the Caesar 2 model. So let's see if we play off the response of the Caesar 2 model as we show the pressures or the unbalanced forces arising in the BOSfluids model. So you see the BOSfluids model. See here, what's the force that's arising in this line? You see the force is increasing. It goes to around 10 kilonewtons, and then we see the line start to move. See the response of the system. See here. And we can see this movement of the line is similar to that seen in the failure. Okay, so you can see the mechanical behavior was similar. For example, the displacement of the line is what you would expect given You can see the guide restraints. And that means we could then get a reasonable confidence that the stresses that were arising in the bends, and also the loads and other couplings, and also restraint joints were realistic of what happened during the failure. And then we could advise the client on whether he should also check the integrity of other components in the structure, and not just those in the immediate location of the failure. BOSfluids could also be used, we also used to provide advice of how they could prevent the failure in the future. Without going into detail, first option was to try and regulate the filling. So I had a regulator valve which controlled the pressure of the fluid that was being supplied to the system. So it was not running straight from the pump pressure head. And that second option was to add a surge vessel or an extra volume that acts as a dampener downstream of the air valve. And this is one of the partial multi-phase elements, as we combined an air pocket within the surge vessel, which is compressed as fluid rushes into this component. Okay, so hope you've enjoyed seeing that example, and I'm now going to pass back over to Chris.
Okay, thank you, Richard. Very nice and a very interesting example. So what have we seen here in today's webinar? Well, we've seen in summary that BOSfluids can be used together with Caesar 2 to prevent surge problems happening in your piping system. Examples shown on the left-hand side again are examples of the types of failures that we could see. And we can try to avoid problems due to things such as flow reversal, very high, very low pressure, pressure imbalances leading to imbalance forces, and of course therefore pipe movement, and also pipe vibration due to acoustically induced vibration and slow flow in the lines. And this workflow can be used for either understanding a failure in the field, as happened in Richard's example, or perhaps a better option would be to try to prevent a failure such as that at the design stage. If BOSfluids would have been used along with Caesar 2 at the design stage of the system in Richard's example, then the failure may well never have occurred, which is of course preferable. So with that, I'd like to thank you for attending today's webinar for BOSfluids and Caesar 2. And I'd now like to open the floor to, are there any questions? So Marjolaine, are there any questions being entered in the chat box?
Thank you. Thank you very much, Chris and Richard. Yes, we already received some questions. Just a reminder, so please use the question box on the right-hand side of your screen to type in your questions. So we can get started with the first one. So you said that BOSfluids gives more information than Yukovsky pressure. Can you elaborate a little?
Yes, we can. I think I will allow Richard to elaborate on that.
Thank you.
Can we go back to that slide then, Chris, just so that everyone can see which slide was being asked about?
So I'm going to jump very quickly back through the PowerPoint then, and it's actually quite a long way. Here we go. This will be the one.
Okay, so what did Chris show on this slide? What Chris was showing on the left was a detailed BOSfluids result, where we can see the pressure versus time, whereas on Joukowsky's simplification, we're just showing a simple pressure value. So for example, let's look at a typical case. We'll be looking at density. If we're looking at a water system, density would be 1,000, speed of sound would be around 1,000, and we'd have velocity, say 1 or 2 meters a second. So then we're looking at pressure around 10 to 20 bar, which is a very large pressure. However, Joukowsky simplification relies on fluid being brought to immediately to stop. So if you've got your valve, you close it infinitely quick. So it's the maximum possible pressure rise that can occur. However, in reality, most valves are not closed instantly. You're at least closing them in around 1 second per inch. And that will give you a much lower pressure than if you use the Joukowsky simplification. For example, the case on the left, where you see there's a pressure rise the order of 5 bar. Additionally, you're also getting from the BOSfluids result on the left, you're getting a frequency component. And this frequency component, if you see here, it's because the wave's oscillating back and forth, got a frequency of around 4 Hertz. And this 4 Hertz frequency could also excite mechanical resonance modes in your system, which means that the stress response could be larger than if you applied that as a quasi-static constant load, which is why it's vital to use the time history solution rather than applying these loads in the static solution in CESA 2. I think that's... Do you want to add any more to that, Chris?
Oh, I think you've elaborated on that pretty well, Richard. Thank you.
Right. Thank you. So let's move on to the second one. So how much information do I need from my process department if I am to do a search study?
Okay.
Again, I think I'm going to hand over to you, Richard, to answer that one as well.
Yeah, so typically when we're doing a project, I think what's important to know is what are typically, we do this as a piping engineer. So we're at Dynaflow, we're predominantly piping engineers and piping and stress engineers. So typically we would ask from the process department of our clients, we would ask for the pressure boundary conditions. So we'd have an idea of what pressures are upstream and downstream of the system. So for example, is it exhausting into atmospheric conditions? What are the characteristics of the pump? What's the running speed of the pump? That will determine where you are, what's your pressure into the system. And also as much information as possible about the valves. And most importantly, the flow rate and the actual pressures in the system. So that's important to note, not necessarily the operating and design pressures you get from your isometrics or specification sheets, but actually the pressure that's arising in the system. If you remember from the system we showed you previously, there's quite a long system to that location of failure, and their pressure differences through the system would have a significant impact on what the pressure is and what the resulting pressure wave would be. Anything else?
Thank you, Richard. Yes, so we received many questions actually. So the next one will be, could you please give us some more details about the difference of water hammer analysis and surge analysis?
Do you want to take that, Chris?
Well, maybe that one will be better to take offline. We will answer all questions that come in. We will answer if we don't get time to answer them right now. So we will provide answers in writing. So
no, but
maybe that one will be better, unless you can answer it perhaps quicker than what I was.
No. So a water hammer analysis and a surge hammer analysis, we use the two words interchangeably in this presentation. And there are in some departments also that, for example, if you close a valve and you've got a pump pumping towards that valve, then the pressure, you'll have two effects. You'll have so if you've got a valve, it's pumping towards a valve, and that valve is closed, then you have two effects. You have the quick short-term effects, which is what we're trying to simulate in BOSfluids, that you've got the fluid being brought immediately to rest, and that leads to a pressure wave that travels back and forth through for the system. But then you also have the sort of quasi-static rise in the pressure, because eventually, because there's no outflow from the system will come to stand at the same pressure as the pump outlet pressure. To close out pressure of the pump, let's say, if you've got a centrifugal pump. And then that slow rise is also sometimes referred to as surge. That's how we would understand that question.
All right, thank you, Richard. So maybe let's take the last question of today's webinar. So if I import from CESA 2, how does BOSfluids recognize C nodes in my model?
Okay, so we've got...
Okay, so how does BOSfluids recognize C nodes then, Richard?
Yeah, so what that would be, I think, because this was a common problem when we started in the system, we often use, I assume the user is similar to us, that we would use C nodes for coupling with what are the values from nodes when you've got flange connections or restraint connections on nozzles. And when you import the geometry from CESA 2 into BOSfluid, it doesn't use all the nodes that you have in CESA 2. So all the restraints, it will clean up the model, a long section of pipe. What it will do is it will remove all the couplings between all of the restraints, and it will make that one section, but with some intermediate smaller elements that are used for the solver in BOSfluids. And with C nodes, it will look at what's the general piping direction around that and combine the C nodes into one value, one node.
All right. Thank you, Richard.
Thanks, Richard. Thank you.
All right, so we have several questions that have not been answered yet, but the time slot for this webinar is coming to an end. So we provide everyone with answers by email after the webinar. So now I'm now handing back to you, Chris, for the last slides for today's webinar.
Yes, thank you, Marjolein. So just before we finish up and close this webinar, I'd just like to, first of all, invite you, if you do have any further questions or comments or any further interest in BOSfluids, then please don't hesitate to contact us. My contact details are on the screen here, and of course, if it is a more technical BOSfluids related question, then I can hand over any questions to Richard and the team at Dynaflow Research Group. So I'll just leave this slide on here for a few seconds to give everyone viewing the webinar here the opportunity to write down my contact details. And as I said, feel free to contact me for any questions or any more information that you require on BOSfluids or CESAR 2 or any of the Intergraph CADWorks and analysis solutions. Okay, and before we finish, what I'd like to do is invite you to and remind you about the Hexagon Local Live event that is occurring, the Hexagon Local CAU, CADWorks and Analysis University 2016, which is happening in Houston in September, later this year, September 19th and 20th. And in particular, the Drivers of Success competition, which is now open, and give you the opportunity to share how Intergraph CADWorks or CESAR 2, PVLeet or GT Strudel have helped you successfully complete a project and help you meet your design and engineering goals. And if you enter in an interesting project, then you can win, and the first place winner for each product category can win an all-inclusive trip to the Hexagon local event. So you have the opportunity to attend world-class training for free and also to share your experiences and also get some get your company and your team out there and get your name broadcast and a bit of advertising. And of course, you also win a prize as well. So the web address to enter if you are interested in entering this, and I urge everyone to enter this for any interesting project that you have completed with any of our CADWorks and analysis tools, please follow the web address shown at the bottom of the screen here on the coaid.com website, the Drivers of Success competition. And finally, if you want to learn more about Intergraph CADWorks and analysis tools, please go visit our microsites shown at the links here on the screen right now. One for CADWorks and one for the analysis solutions. And with that, I'd like to thank everybody for attending today's webinar. I'd also like to thank Richard for your help with presenting the webinar today, and also Dynaflow Research Group as a whole for helping and providing the example that we've shown today. And thank you to you as well. So with that, thank you everyone for attending, and goodbye.
Goodbye. Thank you.